Right. All right. Well, this week's experiment really involved the reduction of benzophenone. The starting material, really, we had benzophenone and we dissolved that in methanol. We made sure we cooled the reaction mixture because once we add sodium borohydride, which is the reducing agent, the reaction is exothermic. So we wanted to make sure it's on ice. And then to monitor the progress of the reaction or whether the reactants, really the starting material, has been fully converted into product, we use a new technique, which is known as thin layer chromatography. It's new in our lab. You know, this is the first week you encountered it. So today's Zoom session, I guess, will focus on using TLC, right? And then we used vacuum filtration to retrieve the target compound, and it was characterized using IR. Any questions? All right, hopefully all of you within the chat have watched the video on web courses because it helps, connect with the actual experiment. I have to move away the participants and the chat. All right. So one technique that we use in organic chemistry is thin layer chromatography. It's a technique that allows us to separate molecules within a reaction mixture, within a mixture. And typically and generally in chromatography, we have two phases, a stationary phase and a mobile phase. But right now we're specifically going to focus on TLC, where the stationary phase is a plate that has a rigid backing, typically either glass, aluminum, or plastic. And what's coated on it, one type is having a thin layer of silica coated on that plate. We call that a silica plate. And then we have a mobile phase, and that's typically the solvent system. You use a mixture of solvents or a single solvent system, but we'll talk about, what type of solvent system do we typically use. So how do the molecules separate? If you saw the video, you would have noticed that the TLC plate was spotted, and then we put it in the solvent system, and then they basically separated or moved up the plate. Well, those molecules separate based on intermolecular forces, based on their interactions with the stationary phase, or which is basically the silica, the layer of silica on the plate, or the mobile phase, which is the solvent system. And I'm not sure how many of you looked up what would the silica plate look like, but it's coated with a thin layer of silica that looks like this. So now if we think about the molecules being separated based on intermolecular forces or interactions, you could right away think about something being polar versus non-polar, right? Something having a dipole moment versus molecules without a dipole moment, right? So we could think about it in terms of polarity. So if you think about the silica plate and the coating, which is shown right here, what type of intermolecular forces are possible? If you have a molecule, placed on a silica plate, that molecule, whatever molecules you have within the mixture, are going to interact with the silica plate based on different intermolecular forces, right? You have a hydrogen attached to an oxygen, right? Hydrogen bonding can happen between molecules where you have nitrogen, oxygen, or fluorine, and they're all next to each other within the second period in the periodic table. NOF, so if you have, let's say, a water molecule, right? OH, NH, FH, those could be hydrogen bond donors. And if we have an oxygen, that could be a hydrogen bond acceptor. Then we could have, one type of intermolecular forces is hydrogen bonding, right? You could have dipole-dipole interactions as well. All right, so it's based on their interactions with the actual plate. So it could have, it could interact with polar molecules. It could form dipole-dipole interactions. It could form hydrogen bonding. So polar molecules will tend to have strong interactions with the silica plate, whereas non-polar molecules will tend to have weaker interactions with the silica plate or with the TLC plate. So now the solvent system plays an important role in moving the molecules that are spotted on the plate, right? So if you spot a molecule right here on the plate, that molecule will move up the plate depending on its interaction with the actual plate. If it has strong interactions with the plate, it'll move very slowly. If it has stronger interactions with the solvent system, mobile phase, it'll move along that mobile phase, right? So that's just an overview. Oopsie. Okay. Any questions so far? I don't see the chat, but Brittany and Nick are here. So if you type anything, they'll be able to see it.
There haven't been any questions as of yet, but I did want to comment on with the silica structure. There's, as you were saying, the two factors at play here. There's not only how much the molecules show affinity to the plate, but also how much the molecules show affinity to the solvent system. And that's why we have this ratio of a polar solvent like ethyl acetate and a non-polar solvent like hexane. And by adjusting these ratios, we can fully control the amount of separation. And that's really what we're trying to do here with the TLC. There's no absolute measure of how far a compound should go on a plate. That's a completely relative number. All we really want to see is a good separation between compounds that aren't our product and compounds that we believe are our product.
Perfect. Yes, we're going to get to that. Thank you, Nick. Okay, so let's move on. All right, so how does the process take place, right?
Real quick question on that last one as well from Maria. The stronger something interacts with the plate, the stronger something will bind to the plate. And so strong interactions will not allow the molecule to continue traveling up the plate, whereas a weaker interaction doesn't very much care for the plate and will simply flow along with the solvent material. Perfect. Does that make it clearer for you?
So Nick, if you ever have a question, make sure you read the question as well or restate it, because once the video uploads, they won't see the question.
Right. Okay. So they can't see the comment sections after. All right. So the question was, what did you say about stronger interactions moving faster and slower up the silica plate?
Okay. Perfect. Thank you. All right. So how does the process really take place? As you saw in the video, what we do is we take the TLC plate, we draw 1 centimeter from the bottom, and then we spot the TLC plate with our whatever we need to spot it with. In this case, we took, while the reaction was still on ice and taking place, we weren't sure if all of the reactant was converted into product. So what we did is we took a small amount, we took a few drops, I think we took 10 drops of the reaction mixture, we diluted it in a solvent, and then we went in and we spotted it on the TLC plate. But to know whether that reaction mixture has been converted into product, what we had is also 2 standards, one of the starting material, and we spotted that as well, and one with the product, and we spotted that as well, right? Once that is set, what we do is we develop that plate in the mobile phase. Okay, so we really take our whatever solvent system we use, and in our specific experiment, we used a 3-to-1 hexane to ethyl acetate. right? Let me go back. Right, and we take the TLC plate and put it right within what we call the development chamber, and we simply put a watch glass on top to avoid the solvent from evaporating, and we watch that solvent move up the plate, right? So you watched it in the video and it was timed like fast, but you saw it moved up the plate, right? And once it moves 50 to 75% off the plate, you could remove that plate, and right away what you want to do is mark where the solvent line is. Okay, so now those molecules will move up the plate based on their interaction with the solvent system and based on their interactions with the mobile phase, right? So why, what's the idea of running a TLC? Um, Not only could we separate molecules within a reaction mixture based on their relative affinity or interaction with the TLC plate and with the solvent system, but we can also compare what we call the RF value based on whatever solvent system we have. So our starting material, if it moved up the plate for a specific value in a specific solvent system, it has a specific RF value that is known, right? And we'll know that our product is formed based on comparing it with the RF value as well, right? And to calculate the RF value, what you take is basically the solvent front, and I'm just gonna, make it simple. Um, Suppose that is 10 centimeters, and suppose your starting material, and you're really taking a ruler and measuring the distance from the line where you spotted it, how far it traveled up the plate, and suppose this traveled 4 centimeter. To calculate the RF value, you take 4 divided by 10, which would be 0.4, right? So a reaction mixture, if we spotted it right away before anything, when only a few minutes have elapsed, we might see that we still have some of the starting material. And if the product, let's say, has an RF value right here, and we see another spot right here, it means the reaction hasn't really reached completion. We still have starting material and product within a reaction mixture, right? So it could be used to monitor the progress of the reaction as well. And we're comparing it to given or known RF value based on that solvent system. Okay, so now now we have to go back and consider, did it make sense how far the starting material traveled up the plate compared to the product, compared to our reaction mixture? And what we could do is take a look at the molecules that we are dealing with and their type of interaction with the silica plate. So if you consider benzophenone versus diphenyl methanol. That's our starting material, and that's our product, right? That's S, and that's P, and RM is a reaction mixture, whatever we had in the flask, right? All right, and we know that the silica plate, based on looking at it, it could form hydrogen bonding, which is a strong type of intermolecular forces. It could have dipole-dipole interactions um, between the phenyl ring and the silica plate. That would be London dispersion forces, weak intermolecular forces, because it's non-polar, whereas the silica plate is polar. So now if you compare the polarity of the substrate and the starting material and the product, you have a carbon-oxygen bond. So you have, a dipole moment right here. So you could have dipole-dipole interactions with the silica plate, right? And you have a dipole moment right here as well. But if you notice within diphenyl methanol, you also have an OH group, right? That is a hydrogen bond donor and acceptor, whereas the carbonyl oxygen is a hydrogen bond acceptor. So there's slightly stronger interactions for the product with the actual TLC plate. Does everybody agree? Because right here it could be a hydrogen bond donor as well as a hydrogen bond acceptor, whereas in the case of the carbonyl oxygen, it's only a hydrogen bond acceptor, right? It's a hydrogen bond
So,
acceptor,
question
whereas
from
in this
Jasmine.
case is a hydrogen bond acceptor as well as a hydrogen bond donor. Yes, go ahead.
Okay. So would the product stick more to the plate because it's more polar? In general, yes. Silica is used for separation that we call normal phase, which just means that it is separating polar compounds from nonpolars with an affinity for polar compounds. There is a type of separation called reverse phase, where we are looking to separate nonpolar things by columns that are high affinity to nonpolar compounds. So it is relative to what you're doing. TLC is primarily used for normal phase separation and therefore will always favor holding on to a polar compound. And also another comment on just the relative affinities is not only is the OH an acceptor and a donator, if you look at the number of possible interactions that an OH bond can form versus the number of possible interactions that a carbonyl can form, the OH bond can form one additional bond. That is due to the 2 electron groups and the hydrogen versus the 2 electron groups on the oxygen. It's not a hard science. It's a relative scale, but it's a useful means of predicting where something should show up on your plate.
Okay, perfect. So with the product, you have the alcohol, so it's also a hydrogen bond donor. So it has a slightly stronger interactions within the plate. Okay, so, and if you actually compare that to the actual TLC plate, you would have noticed that the product was slightly lower. Actually, let's go back. So it has a slightly stronger interaction. So if the starting material moves, so if you develop it and then you have the solvent line and the starting material, moved this far up the plate, you'll notice that the product will move slightly lower, right? How much, or the one that has weaker interactions with the plate will have a larger RF value. The molecule that has stronger interactions with the plate, it'll move slower up the plate, so it'll tend to have a smaller RF value, right? So looking at the RF value, you could also discuss which molecule has stronger interaction with the plate, right? So now, if we are using a solvent system that is completely non-polar, right? Molecules that are polar will move very slowly up the plate, or they may actually remain right where you spotted them. And that's why typically the solvent system is, a mixture of a polar and a non-polar solvent, right? That way it allows both molecules to move up the plate, but their separation and how far they move up the plate really depends on the solvent system. And you might change the ratio slightly from a solvent system being like 8:2, polar to non-polar versus 9:1, and then that might affect the actual RF value, right? Or the separation that you actually see within the plate. All right. And we are gonna move along. All right. So now, while the reaction was taking place, we said that we took a small amount, diluted it, spotted it on the TLC plate. So suppose only 5 minutes of the reaction has elapsed, and you went ahead and took a small amount, spotted it on the TLC plate, and allowed it to placed it on the development chamber and allowed it to develop. Right? You have the starting material, want to up the plate on a specific RF value. You have the product spot as well. And then you have the reaction mixture. And the reaction mixture in this case showed 2 spots. What would that tell you? right? You have two spots. One spot has a similar RF value as the starting material. You have another spot that has a similar RF value to the product. It tells you that within your reaction mixture, you have both the reactant and the product, right? So not all of the reactant has been converted into product. So what that typically tells you is that you would need to let the reaction run a little longer, and then you could take another TLC plate. But by the time you ran this reaction, and by the time you ran this TLC plate, let it develop, and then take a look at the spots, the reaction has been running for another 10 minutes. So you could go ahead and take another TLC plate. If that was 5 minutes, that would most likely be around 15 minutes or so. And then what you see is only a single spot that has the same RF value as the product. So that tells you that all of the reactants that you started out with has been converted into product, because when you spotted it, the only spot that you see is that of the product, right? Okay, any questions about that?
No questions.
Okay, is it clear? Or do you guys just not have any questions because
Chat is currently discussing how the lower RF values correlate to a stronger interaction. It seemed like that wasn't completely clear, so I'll comment on that. The original question is, smaller interactions will have a larger RF value, and that was corrected as in, actually that is correct, that if something is weaker, it will travel further up the plate. So another way to think of the RF value is as a percentage. What percent of the plate did the spot travel up? Did it travel up 60%? Did it travel up 70%? And so if it didn't go very far because it's stuck and the mobile phase can't move it, it's not going to get very far. It'll get 10%, 15%. But something that really has no affinity to the plate is just going to travel with the solvent layer, could be all the way up at the front. It would be at 100%. That's not good. We don't like that, and we'll talk about optimization later, but that should help clarify the RF number.
All right, just keep in mind the lower RF value means it moved, slower up the plate, and that's because it has more interactions with the actual plate, right? Compared to the solvent system.